Our Regenerate, Restore, Reclaim webinar series that we are bringing to you in cooperation and funded by the National Wildlife Federation grant. The goal of the grant is to help provide data, soil testing information, and resources for middle adopters to implement soil health practices on their fields. And today we are really excited to have some guy named Rick Haney on here. So Rick, can you introduce yourself and give us a brief history of how you got involved in soil health and agriculture in general?
I'm married to Dr. Liz Haney, and I got involved in farming when I was in.
Yeah, how'd you get involved in soil health?
Soil health. Well,
Yeah.
Well, I went to graduate school to try to do something with my life, and ended up getting in at Texas A&M, and ended up getting my master's and PhD there. And stumbled across this fascinating thing called soil biology. And not knowing all that much about it, I was fascinated that the soil is actually alive and that it's actually talking to us, and that we could actually learn something from it if we learn how to listen. So that led from one thing to another. And the first big keynote thing was the discovery, well, not discovery, but observation that you could take soil, dry it, and re-wet it, and it would give you off this bunch of CO2 that was directly related to the fertility of a given soil. And that was very eye-opening. So that, to me, was soil talking to us. And now we had a means with which to listen to what it was trying to tell us. This goes along. I get a job with USDA ARS and continue to develop these ideas, simple ideas like when it rains water, that water actually goes into the soil and makes a solution, water extractable, organic carbon, nitrogen, these types of things we'd never done before, didn't have the equipment to do it. And so it was a long drawn out process. Then I run into Ray Archuleta, who was very excited about the soil testing stuff I was working on. And after I met him, things kind of just took off. NRCS was real interested in this type of testing and something different. And it just kind of snowballed from there.
Okay, so let's go back to soil respiration and what that means as far as you said, the health of the soil, and go back and relate soil respiration, microbial activity, and nutrient cycling in less than 5 minutes. I'm just kidding. Take as long as you want.
Okay, so the sun shines, plants use that energy, sequester carbon, dump carbon out their roots, eventually die, become carbon sources. Microorganisms feed on that, like our 12-year-old daughter did recently at Golden Corral. So that's kind of the thing that happens that's so intriguing to me. But what fascinates me the most about soil respiration is that it's not fake. It's not an anomaly. It's there because the food is there. They would not be respiring like they are if they didn't have a food source to drive that system. And so to me, that's an indicator of so many things. It's the quality of the food, the quantity of the food, how much they like it. They're trying to tell us something. Now we can put sugars down in soil and get a big respiration, but that's because they like that kind of food. It's easy to digest. They break it down rapidly, and they do these things. But in the real world, where the soil is naturally running and functioning at a good high level, you get nutrient cycling. Carbon and nitrogen are married together. You can't really cycle carbon without cycling some nitrogen, because that's the way the system is designed. Does that mean anything? I don't know.
Yeah, that was pretty succinct. But so how do you go back to how do you measure that in the laboratory? How do you measure the respiration?
We started out back in 2,000 years ago, right before agriculture was invented, using something called the titration method. And whereas we put this little alkali trap in a mason jar with some soil that had been wetted up, and that little trap would suck the CO2 out of that jar and put it into that little alkali trap, and then we'd back titrate that. It was really an antiquated mechanism, but it gave pretty good results, and we could kind of track things with that. Later, I found at grad school a respirometer that measured the gas directly, that was about the size of a small truck and had one channel and had a piece of paper that, rolled out for about 40 miles, and started charting that and started doing that kind of stuff. And then, of course, technology moved along, and then Solvita came along. I had a pretty big hand in helping develop that. And then after Solvita, the infrared gas analyzers became more and more miniaturized and more sensitive. And, then, so we moved on to that, because that was, you were measuring that directly. Now, my buddy Alan Franzlubers, he still loves titration, and bless his heart, he can sure titrate those all he wants to, but we really do like to measure that directly with a gas infrared analyzer.
So what does that mean as far as laboratory testing, and why do you prefer the infrared gas analyzer over hand titration? And can you tell me more about the differences in those two methods? Because I think that people talk about this maybe in certain circles, and what those differences might be between the two tests.
Well, the infrared gas analyzer is real simple and straightforward. I mean, you just basically run pump the gas right through that sensor, and it's calibrated to give you CO2. It's really quick. It's not labor intensive. Titration is labor intensive, and you end up with some fairly toxic chemicals at the end, and that you've got to dispose of in some way. So it's just not very convenient to do titration. But an infrared gas analyzer is just simple, straightforward, clean, not a big deal. I mean, you're running it through an infrared gas analyzer that's very, I mean, these things used to be, 2 foot square, and now they're, about that big. Some of the sensors we're using now, so they've come a long ways. And what was the question again? Is that the difference?
Well, yeah, and the scalability, and realistically, if we want to determine microbial activity in soils on a large scale, what's the best way to do that, as far as put through in the lab?
Yeah, it's another, it's throughput. I mean, you can run 200 or 300 soil respiration tests a day pretty easily. You kind of get tired of connecting the jars, every jar, to the respiration device, but that's really pretty simple compared to titration. Whereas you're studying an endpoint, and you're using all these chemicals, and it turns color, and you have to hit it right. You can't put too many drops in it. It's just a little more labor intensive, and you really have to pay attention. Whereas my former boss, Darren Harmel, could actually run an infrared CO2 respirometer, because, we made that pretty simple.
Nice dig on Darren. So you kind of like jumped over a few of my questions that I was going to go through as we got into that, but like, what if you get a lab result back and you've run the Haney test, and we'll talk about maybe how that was named in a little bit, but if you run the Haney test and you get respiration scores back, it'll say 1 day CO2. What do those numbers mean? What's a good value, a bad value, and how does that affect really in field of farmers' decisions?
Well, again, to me, soil respiration is the most important measurement that we have, especially as quickly as we can do it. I mean, you can actually do it out in the field in real time, and it just tells us so much. I mean, without rest, I mean, if all of us were in a room right now, we're all taking in oxygen and giving off CO2, and we could get a pretty good estimate of how many of us were in the room based on those readings. And it's not dissimilar to the soil outside. The more microbes you got, the more active they are, the more CO2 they respire. But the other thing is, so you have to have moisture, you have to have nutrients, you have to have carbon, you have to have all those components to be able to get a respiration number. Now, we can spend a lot of time trying to figure out what everything means, but everything is also dependent upon where you're at. I'll guarantee you your CO2 respiration in a field in Minnesota right now is going to be quite a bit different than it is down here in Texas. One of the beautiful parts about that simple test is that you could take a sample, even if it was frozen, and dry it out and send it to the lab, and they dry it and grind it and get a respiration value. Because when they go dormant, when microbes go dormant due to lack of water or lack of temperature, they have this microbial biomass there. And when water shows up and all these other, the temperature increases, they go to work like right now. We used to think that it took, along several hours or days before microbes would respond. They'll respond right now if the conditions are correct. And that's a very key important thing. As far as, what's good, what's bad in a sand, 30 part per million is pretty good. In a soil in Iowa, 30 part per million is not very good. So it really depends on where you're at and what you're doing. And what struck me about that most is back in the 90s, I got to go to Alaska for the first time. And like an idiot, so friend of my friends flew me out into the tundra. We got in an airplane, took off from water, flew to the interior of Alaska, landed in some lake out in the middle of nowhere. He told me we were probably 500 or 600 miles from any human being. So I go out in the tundra and take samples and put it in a baggie and take it all the way back to Texas and ran that thing. And it was like 30 or 40% organic matter, something ridiculous. And the 1 day CO2 respiration was 12. So that's a case where there's an enormous amount of carbon, but it's not, active. It's not being acted upon. So, we have to have all these other contexts to understand what we're looking at when we see respiration scores. Generally speaking, I like to see them above 60 or 70. I really prefer them to be around 150 to 200. Those are in some really healthy systems. Pastures, native grasslands, we should see those numbers up pretty high. Versus if we're in conventionally tilled fields, we'll see, 10, 12, 15, 30 part per million, not too much. But we always like to look at that in conjunction with the water extracted organic carbon, the organic nitrogen, the amount of nitrate that's there, organic matter. So we have to take all that kind of in context.
Okay, so you said something about in conventionally tilled fields, you would see lower respiration than, say, in a prairie situation. So what are the field conditions that are determining the lower microbial activity?
Well, tillage is a fairly destructive thing, especially from a fungal component. However, we have seen, and I've given this example before many times, we got soils from some farmer many years ago through the lab, and they were marked no till and conventional till. That was 2 samples, and that's how they were marked. And the conventional till soil came back, I think it was around 80 part per million CO2, and the no till came back around 40. So he was shocked, and he was like, your test is screwed up. Of course, he blamed the test right away because, I guess I had a hand in developing it. So he knew it was wrong. And I asked him a couple of questions, and I said, well, how long ago did you till the soil? And he's like, well, about a week ago. And I said, well, what about have you done anything to your no-till? He said, well, no, not a thing. It's like, well, when you till it like that, you release all of this carbon that's kind of been locked up, and the microbes have access to it. You get this big burst of CO2. So again, context is really important, because just because you have a higher reading doesn't necessarily mean it's this or that. It just means it's, something has taken place, which led us to ask him what was going on. Otherwise, we'd have just written that off as the test doesn't work and, it doesn't have any meaning. And the reality is, the microbes are not political, and they don't have egos. They're trying to survive, and they're trying to utilize what's in front of them. And so our job is to put the best stuff in front of them.
So I was actually trying to write something up about that last night, and thinking about how important it is to not burn all of that up with each tillage pass right away. So in my mind, it's like cooking a brisket, right? You don't want to cook a brisket really fast because it's just going to taste awful. So it's like a slow burn. So can you explain, maybe possibly using my brisket analogy, what in a no-till system, what a slower release of nutrients would be if you're not getting that burst of CO2 every time you do a tillage event?
Well, I'll use this analogy. Your brisket as a dinosaur. So fossil fuels, right, are millions and millions of years old, decaying plant and animal stuff. So it's basically, it's by and large old plant material. You know how come we have fossil fuels and we can go down there and dig them and get them? Because the dinosaurs didn't have plows. The dinosaurs that had plows, there wouldn't be any fossil fuels. So we have them to blame for many, many things. But the point I'm trying to make there is that every time we do a tillage pass, and I did plenty of tillage passes in my lifetime, we are disrupting the cycle. We're, changing the system. We're putting aggregates, we're breaking up aggregates. I mean, these are just things that are not how nature does it. You don't see nature destroying its soil or tearing up its soil, except for the soils Darren and I worked on in Texas that are vertisols, and they self-mulch. And what was interesting about that is for 10 years, I had no-till, conventional till side by side. Now, granted, my conventional till wasn't bare more than 2 or 3 weeks out of the year because we had cover crops going, but we never did see much of a soil health score difference between those two systems if we kept the conventional till system covered with cover crops. So even though they self-mulch and do all these things, I'm not a completely against tillage because there's a lot of farmers still doing tillage. We just wanted to get the cover crops in there to feed the microbial biomass, to help them cycle nutrients and put fertilizer dollars in their pocket.
So when you measure, you're not only measuring microbial activity, you're measuring forms of nitrogen and carbon in the soil. Can you tell us what forms of nitrogen you're measuring and why that might be different than getting a conventional test run at a soils lab? Or let's say in states where they don't even run nitrogen, but like to talk about it. Anyway.
Yeah, it really surprised me when I really started looking at the soil testing industry back in graduate school, how many labs in the country and worldwide don't test for nitrogen in any form. And the argument was, well, we don't have any nitrogen in our soil. And so my question to that was always, so if you don't put out any nitrogen fertilizer, it's bare ground year round, nothing grows. And of course, that's not right. To get higher yields, you have to supplement with nitrogen, supposedly. And so, that's a whole different ball game. But what struck me was when I first started looking at all this, it was fertilizer, especially for nitrogen, was the fertilizer use efficiency. When I started seeing all those numbers from all that research where they would add 100 pounds of nitrogen and they could identify maybe 30 or 40 of it that actually got in the plant. And that was eye-opening to me because my question immediately was, well, where'd the other 60 pounds come from? Well, it's coming from somewhere, and it's coming from that organic matter that the microbes are using to cycle and break down and release some of that. But then you start looking, excuse me, a little deeper, and it's like they're only testing one form of nitrogen, which is nitrate nitrogen, maybe two, maybe ammonium, and that's it. Well, that's completely ignoring the vast quantities of nitrogen that are in the organic form, that if you can get your microbes in there working, that can start breaking that down and delivering that, instead of being inhibited or slowed down by the luxury tax of having too much inorganic nitrogen. So that was really eye-opening to me. And I really wanted to get at that because for years and years, we were looking at where's this nitrogen mineralization coming from? With all these gazillions of dollars were spent, lots of time. Well, we're going to figure out where this nitrogen. Well, they never really did. They never came up with a good equation for how much nitrogen mineralization you can get from a given organic system, organic matter. And so then they just came up with, well, let's say you get, if your organic matter is 3%, you get, 20 pounds. Let's just call that good, but we can actually directly measure these things. I'm a big fan of measuring things when we can, as opposed to just guessing. Now, some people will say this is guessing, but it's pretty good guessing compared to some of the other stuff. That the technology wasn't there yet. I knew that, it rained water because it's really sharp like that. I took a whole course on it. And that when that hits the soil, that we have a water soluble nitrogen form that includes the organic fraction, the inorganic fraction. And when they came out with these machines that would do carbon and nitrogen for a water extract, the light bulb went off in my head. And it's like, there we go. Because we can take that sample, a soil sample, extract it with water, run ammonium and nitrate on it for your inorganic fraction, and total nitrogen on the same sample. The difference is the organic fraction that we've missed all these years. And that's money directly in your pocket, whether you're conventional till, no till, whatever till. We have always seen nitrogen, organic nitrogen, in every soil sample we've ever analyzed. And sometimes it's dramatic. Sometimes we're talking about 20 or 30, 40 pounds of nitrogen that we were missing. And to me, that was so critical because, if you think about, farmers don't have a whole lot of control over commodities, over input costs. Fertilizer is the one thing they still can kind of control. And so moving down the soil health path gives them even more control over that. And that was something that really appealed to me.
So yesterday I was talking to a farmer that had run a couple of Haney tests for the first time. And he and his agronomist were like very concerned about the amount of nitrogen that was recommended. They thought it was way too low for what they've experienced before on their fields. And they're in a different state. So they thought that the test was not calibrated to their state and their needs. So can you explain how this works, no matter where you are, what state you're living in, or what your climatic conditions are, and why that nitrogen is actually available?
Well, what our test is, quote unquote, calibrated to, I hate that term because everybody throws that term around like, oh, yeah, our test is calibrated. Now show me the data. I spent 19 years trying to get all these people to show me their calibrated data. It never shows up. Why? Because it's a biological system, which is non-linear. We want to make it all linear, and it's just not. Yields change, everything changes. You get good moisture one year, you don't get. So to sit back and say that we have all this calibrated data is just, not realistic. What we were after with this test was not to calibrate it to yield, but to calibrate it to the missing NP and K that we knew was there that we weren't accounting for. And that was a whole different strategy and a whole different look at, what does this mean? So if you grew 100 bushel corn and it only used 30 pounds of nitrogen you put out, where did the other 70 come from? That's what we were after with this approach.
So does the soil are you there? You cut out for a second. Does the soil pH affect the results? Like if you went to test and do the Haney test on a soil with a pH of 5 versus a pH of 8, is that going to drastically affect the validity of the results, I guess?
Not for nitrogen, it would for phosphorus, for sure. Which brings us back to the other thing, all these different extractants that have been developed over the decades, that none of those extractants, Malic 3, Bray, Olson, ammonium acetate, you name it, none of those had biology in mind, did they? They all had chemistry in mind. So they were all developed in a lab and were not developed from the aspect of, how does biology do this? How does the soil do this? That was never taken into account at all. So H3A was trying to mimic the soil environment that plants actually grow in, to further to the understanding of, well, this is what the plant actually sees as opposed to what we can rip out in the lab, because that really isn't all that helpful. So there's a lot of different things that, as a matter of fact, when I developed that extractant, I was looking for the soil pH actually controls phosphorus availability to some extent. And so I was trying to develop an extractant that would extract near the pH of the soil, because the soil pH is going to be largely in control at how much P and K get extracted. And to give you an example, the soils that Darren and I worked on were pH 8.2, heavy clay, Houston blacks. Malic 3 would extract a pH 8 soil at pH 4. Now that's not realistic at all. And so, H3A will extract that same soil about 7.7 or 7.6. And that's a more realistic. And people are like, well, but the phosphorus numbers are down. And that's correct. They are, because there's too much calcium in the system. So, and calcium likes phosphorus.
And that
so we had to
phosphorus is not really available.
Well, right. One of the biggest complaints is that we had around here was that farmers were putting on phosphate fertilizer and getting yield responses, and Malic 3 said you didn't need any phosphorus. So that was very upsetting to a lot of people. And so, but that's the reason, because it was dissolving calcium phosphates that weren't plant available and saying they were. And so that was a big problem. Olson did a better job on that because it was designed for calcareous soil. It doesn't do very well in non-calcareous soils. So I was trying to bridge the gap between those two things from a more natural perspective.
And just for some background, can you describe what the extractant is that you're using for phosphorus and calcium and micronutrients, and how you develop that?
Yeah, that was several years, several thousand samples of, and there's 4 papers out if anybody wants any of them. But that was, I mean, I had a list of chemicals, probably 20 lines long to begin with, and I just started weeding things out, extracting soil, comparing it to Malic 3 and Bray and Olson. And water was also an important one that I used to compare against. And then it ended up over 10 years being narrowed down to 3. It's malic acid, oxalic acid, and citric acid. That's what's in H3A. And it's amazing to me how much P, K, and micronutrients I could get out by moving the pH of that extractant just a little bit. And what really struck me about that was that plants are dynamic. Plants can understand at some degree what they're seeing in the soil, what they need to do to get more out. So they can change on the go. They can dump different acids. They can increase or decrease the strength of them to meet their nutrient needs. And this is something we just don't account for and have never even really thought about. We just put the fertilizer out there and hope the plant root runs into it, is what we've always thought happened, or I always thought. But it's a much more dynamic process. And this extractant, I think, is a step in the right direction of trying to mimic nature and try to understand what the plant root sees instead of what we just think it sees.
Because those are 3 common plant root exudates, right?
Yeah, I see you lead me. Yeah. So I looked at the research, the literature extensively, and those were the 3 most common found in most the commodity crops across the board. Those 3 were I mean, you could spend several lifetimes trying to develop a soil extractant that really mimicked nature and encompassed all the dynamics of what goes on. And I mean, that, you get nowhere if you had to get the right answer all, to begin with.
Yeah. So we had a good question from Tom, and he wants you to address that after he takes a Haney test, is there any way to know or account for how much nitrogen would be supplied to his corn crop when he terminates a legume cover crop? And is there a test for that, or does he calculate it off of biomass?
Well, for starters, once you terminate a legume, it's not going to be immediately available. this test probably won't show up unless you've terminated it and it's either been plowed under or it's had several months in rain to dissolve into the soil so much, that's going to be almost impossible to account for very quickly, because it's just like in no-till systems. When the cover crop or whatever is terminated and dies back, it takes a while for that to work into the soil. Whereas if you plow it under, now it's fairly immediate. And so, that's going to take a little bit of time. And I don't think you're going to pick that up within a week or two or a month or two of terminating a legume. So for now, yeah, you could try to estimate that off biomass.
Yeah, and I will add that Regen Ag Lab has a cover crop test. So you can get a 2 meter square or whatever you write down, 3 meters, however much biomass you want to collect, send it to the lab. They get percent moisture, and then they do a total digest on it to determine how much nutrients are available in that cover crop. And then they give out a list that compares it to like common fertilizer equivalents, so that it's real easy to understand. But that
I
was
guess I should have known that. One of the fun things that I've got to do since I've been working for Lance is I've had access to all these databases, and that total nutrient dissolution or digest. So we have several samples that have had PLFA run on them, total nutrient digest, and Haney test. And that is absolutely fascinating to look across to see, because there's a pretty strong correlation between what extractable organic nitrogen and total nitrogen. I just looked at that this morning, and it's like, wow, nature really does know what it's doing. Versus if you just look at inorganic nitrogen versus total nitrogen, there's not much of a correlation there. So again, we're not accounting for a whole lot of organic nitrogen that's there. And if you can get the microbes working on it, it's going to help.
So that brings us, since you showed us your shirt, what are you doing now? And what are any new developments maybe that you've come up with recently, since you're looking at all this data?
Well, Lance has got me in this barn captured. So I'm not in Nebraska. I'm currently housed in this barn of my own making. And what he's had me do is he's given me access to the data set that he's accumulated. And so I've been looking at lots of different tests, lots of different values, trying to make sense out of it. To give you an example, PLFA is a pretty popular test, and I didn't know all that much about PLFA, but I'm learning quick because I've seen a lot of data. And so I've come up with a calculation, like the Haney test has a soil health score. Well, I'm developing a PLFA soil health score, which has really been super fun. I have 3 versions right now, and one of them's winning. So I think it'll be helpful that when you get a PLFA analysis that you can kind of look at what it looks like compared to others. We can give you an average. And then it's not keyed on any one thing. It's like the soil health score. It's a combination of results that give you an overall picture. So I've been working on that. I've also been working on this regenerative verified thing. That's a depth analysis to try to help us understand what progress we're making in soil health. Mainly that's the biggest thing. Is I've had so many farmers over the years say, well, how do I know if I'm, headed in the right direction? This set of calculations will really kind of zero in on that and help them understand where they're at in their regenerative journey.
I want to stop you there. Wait, I want to go into that some more.
Oh, good.
So the regenerative certified test, what is involved in that, and like how can that be used for a person that is just transitioning maybe a field from conventional to no-till or implementing cover crops? What kind of information are they going to get?
Well, that whole thing started out with, we were having farmers take samples from their fence line. In addition to their fields, they take several samples in their field and composite them and send those into the lab. we started having them take them out of their fence row because they're not farming in their fence row. And then we'd get those comparisons. And it was absolutely fascinating. We never saw anybody's field that was better than their fence row, not once. And we ran hundreds of those. And so that got me to thinking about how do we do this? And the thing I liked about that is they weren't being compared against their neighbor's farm or somebody in another state, or, you know, it was their soil telling them what's going on with their management. So then we took that one step further. And so now what we're looking at is you take a 0 to 6 inch sample and a 6 to 12 inch sample. And the 6 to 12 is going to be your baseline, basically. You're not going to really affect the 6 to 12 inch layer nearly as much as you are the 0 to 6 with your management system. And so that comparison, both of those get Haney tests run on them. And then we come up with a set of calculations that show how that scores. That doesn't mean that you're good or bad or left or right. It just gives you a score. And if you want to, and what you want to see is that score goes up over time. And that means that you're headed in the right direction. But you can also look at, you know, you can index that and to say, well, you know, above this, you're doing it. And below this, you've got a little bit more work to do. You know, these kind of things. So that's going to be an important thing going forward, I think, because it's really good information, and it's your soil and your climate and your management, you know, and your deal. It's not comparing anybody anywhere else. So that way you can compare soils in New Mexico versus Iowa or Minnesota. It doesn't matter. It's your soil against your management, not anything else. And that's going to be very helpful, I think, moving forward.
Okay, Giddy. We just got like a super cool question from Scott. And he says he's seen studies talk about carbon species. Are there any certain carbon species in the certified test? And are you measuring different is measuring different carbon species really needed for evaluating soil health?
Well, this is just my, you know, humble opinion. I think we can get lost in the weeds pretty quick if we start looking at speciation of different carbon compounds. And, you know, we've made that mistake so many times when we just really need to know, is this soil functioning? Is it working right? Is it doing what it's supposed to do? Is the respiration good? Is the weot good? Is the organic matter? You know, if we're going to run down the rabbit hole of speciation, that, you know, that's going to get really tricky and even more confusing. Now, is that probably an important thing in the future? Maybe so. But we're not doing anything like that. We're looking at, you know, soil organic carbon just straight up. On some of the stuff Lance tests for, they have total carbon, which is also fascinating because, you know, there's carbon and calcium carbonate, so that counts. So organic carbon is really the key that we're after for right now.
Okay, so the Haney test does test for different types of carbon. So it might not be a speciation, but can you talk about the different types of carbon that you tested?
Yeah, I see what you're doing there.
Yeah.
All right. So the other thing that we've done is we come up with a calculation that for farmers that hopefully they can someday sell to some carbon credit company. Now, the big difference between this and everybody else is they're just going off soil organic carbon. That's it. And to me, that's almost completely meaningless because, I mean, it's not. Soil organic carbon is very important, but I want to know how much of that carbon is doing something, you know, cycling nutrients, growing food, doing something. So we've accounted for what we call the dynamic portion, which is, so you got solid, liquid, and gas phases of carbon, and we account for all three of those. And so we're going to end up with a calculation that says here is this farmer's, this is how much carbon is being captured on a yearly basis. And we want to see them get paid in whatever dollars per ton of carbon captured every year. And so as you increase your soil health, that obviously you capture more of that carbon. But we are going to include the dynamic portion, which is the gaseous and liquid phases. So, you know, water extract, organic carbon, soil respiration, because guess what? You don't get soil organic carbon without dynamic carbon. That's what gets it in there. That's what makes it work. And again, let's not account for any of that. Let's just, drive on with our computer models and say, this is good to go. Well, are we going to actually try to do this correctly and account for what's actually there and pay the farmers a reasonable price? Or are we just going to blow it off with computer models and let the AI tell us everything that we're supposed to do? This is the stuff that upsets me. We can measure some of these things and we can account for some of these things. And computer models are great. I'm sure AI is great. But, the dealings I've had with artificial intelligence is nobody can really understand how it gets values it gets. So we're leaning on biological intelligence until that goes out the window. Once our biological intelligence is gone, then we're in trouble.
I want you to back up from a non-science, maybe give us a different perspective in more layman's terms, what is happening to the carbon in the soil as it cycles. So we know it's all pumped through by photosynthesis, but what amount of that is actually going into the soil, and then what happens to it after, and how does that relate to what you're measuring?
Well, and that's the question, everybody wants to have is, what, well, the carbon, the fun part about working in the lab back when I was working for Darren was that we'd have these kids come through and tour the lab, and we'd always go out and get a stock of something that was growing, wheat, corn, sorghum, whatever. We'd pull one of those, bring it to the lab, and we'd ask those kids, 7th and 8th graders, it's like, well, where did this plant come from? And they'd say the dirt. And it's like, well, yeah, that's kind of right. But really, where did the 50% of the mass of this come from? And they would never get it. And you'd say, it's magic. And they would be, what do you mean it's magic? It's like, it came out of the air. And they just were blown away. They just couldn't believe that was even real, but it is. And so, so CO2 comes in, the plants, use that to do lots of different things. They dump it out their roots. They do. And now you're going to get me off on a subject I shouldn't be talking about, which is that I believe there are chemical signatures in soil and in the air that are carbon based that tell plants, warn of predators, warn of, there's so much going on there that we are not tuned into yet that I think is really going to be critical in the future. And so now I've gotten off on, what were you asking me? Walk me through what?
I like that subject there. But what happens to the carbon once it gets into the soil? Like, so 50% of the carbon from the air goes into the roots or root underground system. What happens to that?
Well, I guess this is why I think it's interesting about the water extractable organic carbon versus the total soil organic carbon, because how much of that is soluble. You got this soil organic carbon is this gigantic mass of carbon, and so what I've always been curious about is how much of it's in play. And now they're coming out with some of the stuff saying, what is it? 5 or 6, 7, 8% of the carbon is microbial. That's in the soil, or are the numbers higher than that? I can't remember.
I think higher, but
yeah. Well, anyway, that's what's so fun about. And let me make this fun point. So when we test for carbon in the soil, you got your organic matter, you got water extracted organic carbon, but respiration. This is really important. I should talk about this more. I think I did a research study before I retired that I never published, and I wish I would have. And what I did was I built this device, and I could run 40 samples at once. I called it Frankenbreather. And I was flushing, had all these different soils connected to all these jars. It was all automated. And every 4 hours, it would flush the CO2 from the soil out of that jar, every 4 hours. And what I was looking for is when you dry and re-wet a soil, that soil respiration comes up and it peaks and then falls and then comes to a baseline. And that peak is critical. That peak tells us everything we want to know, whether that's microbial biomass that's been dead and rejuvenated, recycled. That tells us something about the biomass. The speed with which that happens also tells us something. We ran over 400 samples through that system, and 3 of them peaked right after 24 hours. The other 97%, or 397 soils, peaked within 24 hours, and most of them peaked before 12 hours. And so this is why I don't believe that we have to go 2, 3, 4, 5, 6, 7, 8 days of incubation to get CO2. The 24-hour test is by far the best correlated with the peak. That's critical. And so, and tell me how many soil testing labs out there that want to wait 3 or 4 days to get an analysis on anything. Time is money. And so these things are really important, but that peak of that flush tells you so much about that soil, what the nutrient status is, what the biomass is, kind of what are you looking at? The thing and to give you one more example, Darren remembers this, we found soils at the research station up at Riesel, which is 60 miles away, that were in a basement that were taken in 1947 from the exact same plots we had just sampled, that year. Same plots, same soil. They've been sitting in there, dried ground for 65 years. 30% of them came back. We wet them up and 30% of them came back. I mean, big time. After 2 days of incubation, another 30 or 40% came back. Only about 20 to 30% of all of them didn't come back at all. So they were just completely dead. That tells you something about how resilient these systems are, and it should encourage us to work with them more.
Okay, my mind just went down a rabbit hole there. Sorry. About resilience and the microbial community. Because we had a conversation about that the other day. How the soils responded with respiration relative to the amount of water extractable organic carbon there is in the soil, and what kind of carbon is actually in there. And part of that might be the microbial biomass and how well your respiration comes back after a drought, in my mind, is relative to the resilience of the microbial community in your soil. So if you've been growing corn, all you have are microbes that have been evolved to live in that corn root scenario. Whereas if you have a larger diversity of plant roots in the soil, you're going to have a larger diversity of microbes in the soil. And so when a drought does come along, you'll have different species there that will be able to revive after, being in the drought since 1947, and come back alive and rebuild their communities and continue to cycle nutrients for you. That was my long pause right there.
I guess one of the eye-opening things in graduate schools, we should do something called a chloroform fumigation incubation test. So we actually, took a mask with chloroform on it, put it over the microbes, noses, and they died. And so we actually fumigated soils and then incubated them. After we evacuated the chloroform, we let it set for 1 day and then sucked that out of the jar and then incubated them for 10 days and see who came back. And what was interesting is you killed all the nitrifiers. We never saw any nitrification take place after the chloroform was there. So it killed all the nitrifiers. But somebody survived and came back and started chewing on the dead microbes to give you that biomass estimate. And when I started doing the same thing with just drying and re-wetting the soil, I noticed that the curves were very similar in their release. And so I thought, wow, look, so in the 70s, there was something called the substrate-induced respiration test, where they would just add sugars and estimate biomass off that peak, off that flush. Well, drying soil and re-wetting it is a natural phenomenon. And that is basically a substrate-induced respiration test from your soil without adding anything. And that appealed to me. It's like all you have to add is water and it'll tell you. So, we have a tremendous amount to learn about all this yet. We're just stepping through the doorway, I think. And the DNA analysis stuff that's coming on should be helpful. It's going to be tremendously confusing for a while, but it'll get sorted out at some point. So I think the future is bright for all this stuff.
So we had a couple questions. Let's see. The CO2 flush is a symptom of the priming effect, right? The research that Willie's been reading lately shows that the quickest microbial response after drying, rewetting as a priming effect was from fungi and not bacteria. So can you talk maybe about the fungal to bacterial ratio, I think, on what we want for crops and ecology?
Well, that was one of the fascinating things about that little study I told you I never published, was that there were several of those soils that peaked within 4 hours. 4 hours. I mean, so I have all these curves that show the speed with which all these different soils responded. And so some of them responded very quickly, but not all that high, and then sustained close to that. Others shot way up and fell like a rock. And I can't say for sure which one of those was which, but if I would have had more time doing that, I think we could have finally, if I'd have had access to PLFA analysis on those soils, that would have just been amazing, because I think we could have identified which one of those soils were bacterial dominated or fungally dominated. But I didn't have that information, but it always made me wonder, because they were so different. And, so many soils responded in 4 hours, others 8, others 12, others 16, and why? Because, they all had different fuel. And I really can't address what that is or how that works as far as fungal versus bacterial. I can tell you that in the samples that I've seen that have had the Haney test run on and PLFA, that there are not very many fungally dominated soils that have super high respiration. They have good respiration, but not really, really high. That's really more bacterially dominated, some of those really super high ones. And I found that to be fascinating. But you can't make that statement, a blanket statement, that the bacterial dominated are all the super high ones. That's just not true. There's some fungally dominated soils that are very high respiring too. But we've also seen, as soils really progress, have high soil health scores, that their respiration actually lowered somewhat. And I think that is kind of a sign of a fungally dominated soil based on some of the PLFA analysis I've seen. So there's no hard and fast, straightforward answers on any of this stuff. Again, it's not a linear system. So we're still trying to learn some of these other components and plug them in there to give us a better picture of what we're looking at.
Okay, we had another question. Is there any experience using water and carbonic acid and a carbon increase in the soil?
No, I have no experience with that. That was one of the things that we were going to mess around with in the lab was, I did a little bit carbonic acid, used some carbonic acid as a soil extract. But boy, you got to be real careful with the concentration there, because that stuff's pretty wicked. But there's been a lot of discussion over the years about when it rains, you've got CO2 trapped in the soil to a certain aspect because of the respiration. And when it rains, does it form carbonic acid in the soil and act as a soil extractant? And that may very well be. I have no research to back that up.
Yeah, I think that's what he was referring to. But yeah. Okay, here's a really
again, there's a lot of things we don't know that.
Yeah. Here's a fun question for you. NRCS 216 soil health standards do not use the Haney test. Are they using different metrics to measure soil health, or are they moving ahead or past the few years old Haney test?
Yeah, they're using I think that's a reference to the Cornell soil health test. When some folks from Cornell got into NRCS, they made damn sure that the Haney test got kicked out of that. So, that was politics. That had nothing to do with what's right or wrong. That was all politics. And, people want to use Cornell soil health test. That's fine with me. I don't care. I think those metrics are not all that valid because, for example, their ACE protein thing, there's not many autoclaves in the soil that I've seen running around, but, I think those are old methods repackaged as something new, and they're not really all that new. But you know, I'm not saying it's useless or nothing like that. Well, I guess I kind of am.
Okay, there have been a couple of questions on the timing of pulling samples. So when's the best time to pull a Haney test?
My answer to that is, contrary to popular belief, the Haney test was developed to save farmers money or give better results for N, P, and K. So, as an example, over the 45,000 samples we analyzed at the USDA lab, our average savings was $20 an acre for nitrogen. That was huge, and that's what that test was developed for. In addition to a more accurate portrayal of how much phosphorus is actually in your soil that a plant could see, potassium, calcium, iron, aluminum, to look at, you know, pH issues. That's what all that was developed for. So the best time to pull the samples before you put fertilizer out. Now, if you're not using fertilizer, which I doubt that many people aren't, but you know, then take it whenever you want to know something or what you think is happening. Take it before a treatment, and then after, or, you know, take it whenever you really want to, because when you take the sample, when you pull the sample, whether it be spring, summer, or fall, you're going to be looking at what's going on in that soil right then and there. You know, that soils function naturally, and you're going to get some variation. We've had farmers say that, you know, I took a sample this year and a year later I took it and then the numbers were different. It's like, well, thank God. It is a dynamic system after all. And we are so stuck in that if I pull a sample every year from the same spot, that it ought to be the same number. That's ridiculous. Soil is a living system and not a static system. So we should be able to account for that and start to get our heads around that soil biology is variable and moves around a little bit. That should be challenging to us, not, you know, close the door on it.
Okay, well, actually we're at time here. I just want to share some of our upcoming events. This is the first in a 4-part series that we're doing with our National Wildlife Federation grant. Next week, we have Mitch Hora. He's going to talk about digital tools to increase profitability through soil health. He's got the Haney test well worked into his program, and so probably we'll expand on that some more. And then after that, Russell will be on talking about how he uses soil testing on his farm to increase profitability. And then we'll have Adam Darty, who will talk about cover crops and then also his experience with soil testing. He's done quite a bit of PLFA testing as well, and how that's increased profitability for his farmers. We also have an in-person event June 1st and 2nd here in Salado, Texas. We have lots of great speakers. We have Rick, Adam Chappell, Jimmy Emmons, Rick Clark, Russell Hedrick, Lance Gunderson, and probably a couple others. But we hope you can join us for that. You can go to our website at agsoilregen.com to sign up for any one of those. And then if you have any questions, feel free to reach out and email either me or Russell if you need any more information on what we talked about today, or any of the other things that we're doing here. Just reach out and let me know. And thank you, Rick, for being on here. He went video silent there.
Thank you, Dr. Haney.
I'm glad that everybody got to see how the Drs. Haney talk every day. Anyway, everybody have a great day, and we'll see you soon. Well, this is